So we could stop here, but there's actually a couple of issues. Maybe you spotted some of them. One problem is the malicious name server. We still haven't solved this problem. If you are talking to some hacked malicious name server or some attacker pretending to be the name server, they could send you these three values. They could send you a bogus record where this says 6.6.6.6 or some other evil IP. And then they could use their own private key to sign the record. And then they can just provide their own public key as the third value. So you could be talking to an attacker. They could send you these three things. You'd use the attacker's public key to verify the attacker-generated signature, and you would be none the wiser. So we still haven't solved the malicious name server problem. And turns out we haven't solved the network attacker problem either. Imagine if a network attacker takes this message, deletes it, and replaces it with a malicious record signed by the attacker's private key, and we attach the attacker's public key. If a man in the middle drops this packet and replaces it with one of those malicious packets, once again, the recursive resolver would use the attacker's public key to verify the attacker's signature, and the recursive resolver would still get cache poisoned. So we still haven't solved some of our problems. Now, if you hear these problems, they might sound kind of familiar. It seems like everything is coming back to the same problem where somebody could change this public key. They could replace this with the attacker's public key and then sign something using the attacker's private key. So really, all of the problems we've just talked about come back to the fact that you don't really know if this is the name server's public key or an attacker's public key or somebody else's public key. You don't have any trust on this public key. Now, once again, think back to all those cryptography protocols we talked about. Did we ever talk about this exact same problem where we said, I don't know what the public key is, or I don't know whether it's correct, so I can't get any trust? That's something we've already talked about, and we've already solved this problem. So we solved this problem by using something called certificates. Remember, certificates were a way to give trust on somebody else's public key. You could sign someone else's public key to say, if you trust me, I'm signing their public key, so now you know who they are, and you trust them too. So what if we just take that same idea of certificates and bring it into our DNSSEC design? Maybe that can solve all of these problems that we're talking about. So we've taken two cryptographic primitives, digital signatures, and now we're going to bring in certificates. And by putting these two cryptographic ideas together, we're hopefully going to get a good DNSSEC design. So this raises some more questions that we have to answer. Another question we haven't quite answered yet is, how do you delegate trust to a child name server? What if the root name server doesn't know the answer? Remember, they're supposed to say, I don't know, but you should talk to this .edu expert. Here's their name, and here's their address. How do you actually give trust on that? How do you know that you're being directed to the correct .edu name server and not some malicious one? So we'll just do the same thing we did in certificates. So not only do certificates help us solve the public key issue, they'll also be used to help us redirect down the tree. So that's good, and we'll see that in action. And the final question we have to answer is who the root of trust is. So remember that in certificates, in order to know that someone else's public key is trustworthy, you need to get a third party to delegate trust. So if you want to trust Bob, you first have to trust Alice, and then Alice can say, if you trust me, now you trust Tim. So we'll use that exact same idea to go down the tree. You trust me, the root, so I'm going to issue a certificate for .edu, now you trust them. And .edu might say, well, you trust me, I'll issue a certificate for Berkeley.edu's public key, so now you trust them. So the way we'll use certificates and have people delegate trust to each other is based on the tree that we've already built. So we'll just use the same tree that we've already built to solve question number 4. And the final question is, who's at the top of the trust anchor tree? Who do you trust automatically? Remember that in a certificate chain or any sort of certificate system, sometimes called public key infrastructure, you have to trust somebody at the start so that they can spread trust to other people. So who's the first person you trust in DNSSEC? Well, a natural choice would be the person at the very top, and that's the root. So we'll automatically assume that the root is trustworthy, and then they can spread trust down the tree. So all of this is to say we've taken the idea of certificates and placed it right on top of the existing DNS tree, and that gives us a way to pass trust between other people. And when you're passing trust, the way you pass trust is to sign other people's public keys. So this also solves that public key issue that we previously talked about. So it's another nice design feature where everything fits together, and this design solves a lot of our problems. So in English, this is what it might look like. The first thing the root name server has to say is, I don't know, but you should go talk to the .edu name server. Here's their name, and here's their address. This is the same as regular DNS. Nothing has changed. Now this is new. Because we need to delegate trust to the .edu name server, we need to issue a certificate. And a certificate is nothing more than someone else's public key signed by someone you trust. So the root name server says, here's the public key of the .edu name server. Here is me signing it. So now, if you trust me, you trust them as well. So that is a certificate that passes trust on from the root to the .edu name server. And just like before, when you issue a signature, the recursive resolver is going to want to verify that signature. So just like always, the root name server will say, here's my public key, and you can use this to verify the signature I provided above. So this is what delegating trust looks like, and it's using an idea we've already seen, namely certificates.